And now let's work on the absolute problems. The first thing we have to do here is to practice how to graph data sets. And the first question is, what information does the graph contain? And as you can see here, they ask you to plot the, I'm gonna choose red, to plot the temperature on the y-axis, the time on the x-axis. The best way to choose, see, the time is going between 0 to 16 minutes. So it's easy to just pick one square for each minute. That's what I did. And then also for the temperature, you want to choose a square for every 5 degrees Celsius. And start the 0 somewhere in the middle right here. So it fits really nicely on both sides. And then you just do at 0 temperature. I choose another color so you can see it better. So at 0 minute, the temperature is 40. So I went to 0, that's 0 right here. And I went up and then I put a mark at 40. And then at 1 minute, it's 35. It's easy. So please do this. And then we can answer the question. So what information does the graph contains? Like what happens with the temperature of this liquid as the time is going on? What happens with the temperature? And then you got the questions. At 4 minutes after, what is the temperature of the liquid? So we come down to 4 minutes and we go up on the curve and you can see that the temperature is 20 degrees. So this one is 20. At time 12, what is the temperature? So we're going to go to 12 then. And we're going to see that the temperature of the liquid is minus 15. And after this, you can read this off. And how long will it take to cool this liquid from 40 to minus? So it starts at temperature 0, at time 0, and goes all the way to 16. So that's going to be 16 minutes. And then you can read these off of the graph. And you can answer these questions. So I hope then you understand how to do the graph. So now we go down and really start working on radioactive problem. There is a couple of important concepts. The first one is that each parent isotope decay one daughter. For each parent isotope to decay, there will be one daughter isotope created. So one parent decays, one daughter is created. And the other one is, you have to notice that in the rate expression, that the number of decays is not a constant function of time. Rather, the number of decays over a given time period changes with the number of parents still present in the sample. So there is a very simple example. Like if you have 30 students in the class and half of the students leave every 5 minutes. As the minutes are going, it's always going to be less and less students leaving the class. So it's not like it's not a linear function, but it is rather going to be like logarithmic curve. And then the concept of half-life is very important to remember. Half-life is the time required for half of the parent isotope to decay into stable daughters. So here we are. We're going to have to plot the carbon-14. And we have to plot the parent and the daughter curves. And the half-life should be the X. And the Y is the percentage of the isotopes. So I already plotted it because it was easier for me than plotting it with you, because then it would take forever. So I already did my graph. It's a good idea to choose 4 for each half-life down here, 4 square for each half-life, and then 3 square for every 10%. So that's the easiest way to go about. And I plotted the dots for the parent with red, but I drew the line with green, right, as you can see. And for the daughter, I plotted it in black. And I put the parent and the daughter so you can see how I do it. And try to be as close to be precise as you can. I mean, I know it's hard, but try. Because we're going to measure on this graph a lot of things. So now the next thing we have to do here is that we have to define the age of minerals using the curve. We just constructed to answer questions. So it's important that now we're going to use this curve to read off answers. So the first one is that if you have 50% of parents still remaining, and of course 50% daughter have been produced, what is the number of half-lives? So what we do here, we're going to go look at the 50% right here. See? And then we come down and you can see that it's at 1. So I put down already the 1 right there. And if the half-life is 4.5 billion years, then the age of the sample is 1 times, because the half-life is 1 times 4.5 billion. So that is 4.5 billion years old. 4.5 billion. I just put a B and years. Okay? The next one is we have 25% of parents still left and 75% is there. So 25%, I'm coming down to 25. So it's right here. And if I go down, you can see that that's 2. I already put that down. Do you see that's 2? Now, 1 half-life is 713 million. So you just have to add that up, 1.42 billion. So it's 1.42 billion. Because 2 times 713 million years is 1,426 million, and 1,000 million would be 1 billion. So 1,426 million is equal 1.42 billion years. Okay, now what happens when you have 90% of the parents still present? And so therefore I have to go to the green curve because that's the parent at 90. So as you can come down and see, it's about 0.1%. So 0.1 half-life. So it's about 0.1 half-life. And to get the age of the mineral, now we're going to multiply 0.1 with 14.1 billion. So it's really 1.41 billion years. The next one, I'm not going to do it anymore. So at the next one, you have 75% on the parent. So you come to the 75 right here. You come to the green curve and it hits the first square. So that's 0.25, 0.25. And 0.25 times 47 billion. 0.25 times 47 is equal 11.75 billion. And then you can do this last two. It's easy. I hope you understand, so it's not too hard. And now the next problem. Oh, how did you determine the age of the mineral that contains the particular radioactive isotope parent-daughter pair? That you get the number of half-life and you multiply that with the duration of the half-life and you get the age of the mineral. So now we're going to put the relative dating and absolute dating together. And the important thing is that they're using potassium-40, and the half-life of potassium-40 is 1.25 billion years. So this problem starts with this relative age dating figure, and you can see that C is a metamorphic rocks. Obviously, that's the oldest. C is the oldest. And then you got this B, which is a granite. It's a igneous rock. So it's a granite. And that is the next stage because it went through the metamorphic rocks, but there is this erosion surface here, as you can see. And it didn't go out of it. So it's younger than C, but definitely older than anything else. So that's B. And then comes this, we can call it D, this sedimentary rock complex. And then, of course, the last is this dike, which went through all of it, and that is a basalt dike, and it's A. Now, remember, I already told you that you cannot measure absolute age on sedimentary rocks, so we cannot do this, but we can measure absolute age on C, B, and A. So we can do that. And here is the data for this, the data. So we have the number of parents, and it's 7,497 parent atom, and that is the number of daughter, and that's 1,071. Remember, I told you that the number of parents and daughter atoms together always make the 100% of the original radioactive isotopes. So all we have to do is just add them up. So 7,497 plus 1,071. That's 8,568. Now, this is 100%, 100%. To get the 1%, we just have to divide it by 100. So the 1% is going to be 85.68. Now, what is the percentage of the parent atom? It is really easy because all we have to do is 7,497 divided by 85.68. And what I got is 87.5. So this is the percentage of parent. Okay, and then we're gonna divide the 1,071 divided by 85.68, and I'm getting 12.5. So that's percentage of daughter. So that's 12.5 plus 87.5. That's 100. So we did good. 87.5. Now, what we do after this, we go back to our curve, and we're going to see what is the number of half-lives when the parents are 87.5. So let's see at 87.5, that's right here, go on the green, go down, it's 0.2 half-life. So we have to come back down, 0.2. So I already put down the 0.2 half-life, and now the 1.25 billion years, 1.25 billion times 0.2, that's 250 million. So the age of this basalt dike is 250 million years. 50 million. I just put mil. 250 million. When I multiply 1.25 by 0.2, I'm going to get 0.25. But because it's 1 billion, I have to multiply that by 100, so that gives me the 250. Okay, now let's go to the next one. The next one is 11,480 plus 3,827, that's 15,307, 15,307. We divide that by 100, so that's 153.07. That's the 1%. So 11,480 divided by 153.07, that is 74.9999. So it's 75%. And you know, the daughter got to be 25%, but we divided just to make sure that we did it right. So 3,827 divided by 153.07, and yeah, that's exactly 25%. So 25, and we already did the 75/25. It's, oh, I went all the way down. I hate that. I don't like it. It was right here. See, 75/25, that's 0.25. So the number of half-lives is 0.25. So it's 0.25. And 1.25 divided by 0.25, and that is 500. So I got 500 million. So 500 million. And I hope based on this, you are able to do the last one. See, it's 839 plus 2005 17 to get the 100%. You write that down there, you divide it by 100, and then whatever you get here, this divided by that gonna give you this, and this divided by that is gonna give you that, and then this number times 1.25 billion is gonna give you the age here. So the only thing we have left is to answer the questions down there. So the first question, what is the absolute age of the basaltic dike, Unit A? Unit A is 250 million years. And knowing this, you can look up the eon and era. So just bring up a geologic timeline, which has the ages on it, and you can figure that out. And then you can also answer the unit B, that's the 500 million. You can look up the relative age by looking up the geologic times table, and then you calculate the age of the metamorphic rock. What is the most likely age of the coal bed? Remember, we went through the relative and absolute, and you know that the coal bed is older than the basalt dike, but definitely younger than the granite. So you can kind of put it right there, and especially the relative age. What is the most likely? Yeah, I just told you that. And the top sandstone layer, that still has to be younger than the basalt dike. So I hope I could help you really good, and good luck with doing this lab. Bye.